So when we last left off, we had a discussion on hybridization and its effect on bond strength and bond length. And the central conclusion of our discussion was that the more S character our hybrid orbital has, the lower in energy the resulting bond is, and as a result, the higher the amount of energy is required to break that bond. So for example, an sp carbon-hydrogen bond is substantially stronger, it has a larger bond enthalpy, it takes more energy to break that bond than an sp2 carbon-hydrogen bond. We also see an appreciable effect on bond length as a function of hybridization, and we will discuss that now. So in terms of periodic trends and in terms of trends for bond length, so bond length decreases with, in order of importance, increasing bond order. So double and triple bonds are shorter than single bonds. So for example, a carbon-oxygen single bond is shorter than, a carbon-oxygen single bond would be longer than a carbon-oxygen double bond, and a carbon-oxygen triple bond is the shortest. And the reason for that, if we think about this from a hybridization perspective, if we have an sp3 hybrid orbital, we have a relatively long orbital, and as a result, that orbital overlap leads to a relatively long bond. The orbital extends farther from the nucleus. If we compare that to, for example, an sp2 orbital, the sp2 orbital is shorter, it's a little bit closer to the nucleus, and as a result, when we look at our orbital overlap, when we look at our bond, we end up with an overall shorter bond. For our triple bond, we have an even shorter orbital that's even closer to the nucleus still, so we have our shortest bond. Yes, carbon-oxygen triple bonds are often seen as intermediates, and it's also found commonly in carbon monoxide, for example. So, another feature that can influence bond length is our atomic size. So when we look at decreasing atomic size, the smaller the average atomic radius and the individual atomic radius of atoms in a bond, the smaller the bond length. So for example, a hydrogen-fluorine bond is shorter than a hydrogen-chlorine bond. So for hydrogen, we have our 1s orbital. For fluorine, we have a 2p orbital. Okay, and as a result, we have a relatively short bond compared to in chlorine, where we're dealing with a 3p orbital that's farther from the nucleus. And as a result, we have a longer bond as our orbital has to extend farther from our nucleus. So increasing atom size, larger orbital, farther orbital from the nucleus, longer bond. Does that make sense to everyone? Does this trend make sense? Now, in terms of atomic radius, just to make sure we're clear, atomic radius increases as you move down a group and to the left across a period. Okay, so increasing atomic radius looks something like this. So increasing atomic radius. Now, this actually brings up a really important point. This brings up a really important point that I may want to write out here. So if we compare a hydrogen-fluorine bond to a hydrogen-carbon bond, we know that the hydrogen-fluorine bond is shorter. Why is that? If we compare the radius of carbon and fluorine, carbon is a larger atom, has a larger atomic radius. And further, building on that, the carbon 2p orbital extends farther from the nucleus. So we have the 2p orbital, the 2p orbital electrons are farther from the nucleus. Why? Well, carbon has a smaller effective nuclear charge, and as a result, the orbital electrons are less attracted to the nucleus. And because this carbon 2p orbital, the electrons in that orbital are less attracted to the nucleus, they extend farther out from the nucleus, and as a result, we end up with a longer bond. Does this argument look familiar to everyone? Does this argument look familiar to everyone? It's the same argument that we have invoked when we discuss and we considered orbital energy. For example, we established that the fluorine 2p orbital is lower in energy than a carbon 2p orbital. Because the fluorine 2p orbital, we have a greater Z effective, and the electrons are closer to the nucleus. So atom effects also impact the size and energy of our orbitals, which in turn affects our bond length and strength. Does that make sense to everyone? Does that tie things together? Okay, perfect. So everything's fitting together quite nicely. So let's try and let's circle, and I'll do the first 3 examples, you do the next 3, and let's try to indicate which bond is shorter. So in this case, we're comparing a single bond to a double bond. The double bond is always going to be shorter than a single bond for the same set of atoms. Next, we're comparing HBr to HF. Fluorine is smaller, and as a result, we'd have a shorter bond. Likewise, now we're looking at a hydrogen-bromine bond versus a carbon-fluorine bond. So we have a 1s, and bromine is pretty massive. It's 1, 2, 3, 4. 1, 2, 3, 4. Bromine is, its outermost orbital is a 4p and 4s. The carbon-fluorine bond, we have a 2p orbital as our outermost orbital, and for fluorine, we have a 2p orbital as our outermost orbital. So in terms of average bond length, the carbon-fluorine bond has a shorter average atomic. Let me rephrase it like this. We have a smaller average atomic radius, and that in turn leads to a shorter bond. When we have this mismatch between atom size, the larger atom often dominates the bond length consideration. Because again, bonds are the overlap of our outermost bonding orbitals. And if we have this giant orbital, it's going to dictate the length of our bond. Does that make sense to everyone? Does this idea make sense? There's another factor at play going along here. Would someone like to invoke another factor that we can use to explain why this carbon-fluorine bond is relatively short? It's also pretty strong. Serves as the basis for common fluorinated materials such as Teflon. Would anyone like to invoke another factor? So the carbon-fluorine bond, we have small atoms that leads to a short bond. What's another factor related to these carbon-fluorine bonds? Electronegativity, yes, yes. So this bond is polarized, and we can also invoke this idea that this polarized bond leads to ionic-like character, and in turn leads to a shorter bond. Because we have this attractive interaction between our partial positive carbon and our partial negative fluorine. These are not full charges, these are partial charges, but this polarized bond experiences an attractive interaction between our carbon and fluorine atoms. And this attractive interaction, this pseudo-ionic character, also leads to a smaller bond length. Does that make sense to everyone? Does this idea make sense? We've seen this ionic character argument before. Let's take a look now, and I'd like you now to help me out. And let's take about 2 minutes. And for each of these 3 bonds, I'd like you to tell me which of these bonds is stronger. Which of these bonds is stronger? So let's take about 2 minutes, and don't be shy to message in the chat your proposed strongest bond. And we'll discuss this example in about 2 minutes. And let's try to get a few more responses in the chat. And we'll discuss in about another minute and a half. And remember, in general, shorter bonds involving lower energy orbitals are stronger. So let's discuss. So the first example, we have overwhelming consensus that this double bond is shorter and stronger. In the second example, if we compare oxygen to fluorine, which atom is smaller? Which atom is smaller and more electronegative? Fluorine, yep. So fluorine is smaller and it's more electronegative. And as a result, the nitrogen-fluorine bond is stronger and it's shorter. So you can strictly invoke the atomic size argument. Does that make sense to everyone? You can also invoke a little bit of the polarity argument because fluorine is a more electronegative atom. It would have a greater bond dipole. Does this example make sense? Did that address the question in the chat? So you don't have to memorize the tabulated bond lengths and strengths, but you do have to know relative lengths and strengths, because this can tell us which bonds are most reactive, which bonds are the strongest, which bonds are the weakest, and it helps us draw reasonable steps in our reaction mechanisms. So if we compare a carbon-hydrogen to a carbon-carbon bond, so both of these bonds are functionally not very polar. They're functionally non-polar. However, if we look at our main point of difference, if we compare a hydrogen to a carbon, which atom is smaller? Which atom has a lower energy orbital used for bonding? Hydrogen. So we're comparing a 1s to an sp3 orbital. This 1s orbital is smaller. Hydrogen overall is a smaller atom. And as a result, because we have a smaller atom and hydrogen is smaller than carbon, we'd expect that the carbon-hydrogen bond would be shorter and stronger. Does that make sense? The polarity argument doesn't have as much sway in this case as just the hybridization, orbital size, and orbital energy arguments, which are related to atom size. Perfect. Any questions on these examples? And this is important to keep in mind because carbon-hydrogen bonds, in most cases, are pretty hard to break. A lot of research has gone into the idea of taking these relatively non-reactive carbon-hydrogen bonds and functionalizing them. That's sort of the forefront of modern organic chemistry and catalysis. That's the goal that would certainly solve a lot of major, very pressing problems. So if we think about a carbon-hydrogen bond compared to an oxygen-hydrogen bond, so on paper, an oxygen-hydrogen bond, if we think about an oxygen-hydrogen bond, its enthalpy and its projected bond strength would be greater than a typical carbon-hydrogen bond. Let me pull up the figures for you, just so that way we can have a direct comparison. I like to have numbers at our disposal here. Allow me one moment to pull up the tabulated values. So the hydrogen-carbon bond is about a 411 kilojoules. The oxygen-hydrogen bond is 459 kilojoules. One of the reasons why carbon-hydrogen bonds are relatively non-reactive is that carbon-hydrogen bonds aren't particularly polarized. And as a result, it's much harder to engage this hydrogen in chemical reactions. The oxygen-hydrogen bond is polarized, and as a result, if we're just looking at bond enthalpies, this oxygen-hydrogen bond is relatively strong, but because it's a polar bond, it can be manipulated and we can engage this hydrogen in bond forming and bond breaking reactions. So in this case, it's bond polarity playing a role in reactivity. Does that make sense? So it's not just bond length, bond strength, but also the polarity that's important to consider. And we'll talk more about that in the acid-base chapter. So what I'd like you to do now is I'd like you to engage with the following example. This is the kind of example that you may see and that you've probably seen on some of the introductory homework assignments if you attempted them a little bit early. I'd like you to compare formaldehyde and carbon dioxide. I'd like you to tell me the hybridization of each carbon atom, and I'd like you to tell me which molecule has the stronger carbon-oxygen bond, formaldehyde or carbon dioxide. And the reason why I've left so much space is that you may want to justify your answer with a Lewis structure or an orbital picture. So I'll give everyone a few moments, and I'd like you to tell me which of these two molecules has the stronger carbon-oxygen bond, formaldehyde or carbon dioxide. And I really encourage you to think about factors such as hybridization and factors such as atom size and orbital size. So let's take about 3 to 4 minutes to work on this example, and don't be shy to share your responses in the chat. And if you have any miscellaneous questions related to the topic, don't be shy to ask them in the chat or verbally, and I'd be happy to address any of your questions. And let's try to get a few more responses in the chat. And don't be shy sharing your response. And don't worry if necessarily your response disagrees with your classmate. The mere act of communicating your response and talking through your reasoning for a problem can help strengthen your problem solving skills and strengthen a lot of the concepts and your grasp of the concepts necessary to solve these problems. So let's try to get a few more responses in the chat, and we'll discuss in about another 1.5 to 2 minutes. And we're already seeing some responses in the chat that have been supported with reasoning. Let's try to get a few more responses, and then we'll discuss in about another minute. Yeah. So it seems the responses that we've received in the chat look great so far. So let's talk about this. So if we look at formaldehyde, CH2O, formaldehyde looks something like this, where this functionality, just for everyone who's keeping track at home, is known as an aldehyde. As we notice, if we look at this carbon has an sp2 hybridization. If we compare that to carbon dioxide, which looks something like this, our central carbon in this case has an sp hybridization. In general, bonds involving sp atoms are, well, let me rephrase that, sp orbitals are shorter and stronger than identical bonds involving sp2 orbitals. So in turn, carbon dioxide would have a shorter, stronger carbon-oxygen bond. So in terms of our list, first we note that both of our bonds are double bonds, and then we look at orbital effects, and sp, or bonds involving sp orbitals, are shorter and stronger. So if we're thinking about strength, we first look at bond order. Both of our bonds are double bonds, and then we consider hybridization. Does this example make sense to everyone? This concept is really important when we get to acid-base chemistry. Recognizing hybridization and recognizing the location and recognizing the orbitals that make up each of our bonds, that's really critical to begin to understand why certain molecules are acidic, certain molecules are basic. Okay, so let's keep going now, and let's do another example. Let's look at C2H4 and C2H6. And I'd like you to tell me which bond is shorter, the carbon-hydrogen bond in C2H4 or the carbon-hydrogen bond in C2H6. So let's take about 2 to 3 minutes to work on this example, and then we'll come together as a group to discuss. Let's get some responses in the chat, and always try to, in your response, include a justification for your answer. That can help you both develop and articulate solutions similar to the way you'd articulate your solution on an exam. And it also allows me to provide feedback into your logic when solving a problem. And the responses we see in the chat look great. So let's look at these examples. So in C2H4, so C2H4 or ethylene looks something like this. While C2H6, ethane, looks something like this. Now, I'm not asking about the carbon-carbon bond. That it's pretty obvious that ethylene has a stronger carbon-carbon bond because we're comparing a double to a single bond. But if we look at the carbon-hydrogen bond, then we need to consider the hybridization for each of our carbons. In C2H4, we have an sp2 carbon. In C2H6, we have an sp3 carbon. In general, bonds involving sp2 orbitals are shorter and stronger. So in turn, that would mean ethylene would have the stronger carbon-hydrogen bond. The exact same logic that we used in our example comparing carbon dioxide and formaldehyde. Does that make sense to everyone? Is everyone comfortable with this idea? Okay, so let's continue on now, and let's talk about phase changes and intermolecular forces. So the melting point and boiling point of a substance are closely tied to the strength of the interactions, intermolecular forces, between molecules of a substance. So stronger intermolecular forces lead to higher melting and boiling points, lower vapor pressures, and larger viscosities and surface tension. That's why, for example, methane is a gas, while hexanes exists as a liquid at room temperature. Because if we look at the intermolecular forces between molecules of hexanes compared to molecules of methane, the intermolecular forces are stronger between two molecules of hexane compared to two molecules of methane. Intermolecular forces are really critical to understanding solubility, miscibility, and bulk properties of matter. So what we're going to do now is we're going to unpack intermolecular forces and talk about how they apply to organic molecules. Okay, so first and foremost, we're going to talk about London forces. These are also called van der Waals forces, dispersion forces. Depends on when you took chemistry. There are many names for the same intermolecular force. Fundamentally, London forces are temporary dipole-dipole interactions, keyword being temporary, on the order of nanoseconds, picoseconds. These are weak interactions between temporary dipoles formed from the random movement of electrons or changes in electron density from collisions. Dispersion forces are a general type of intermolecular force that occurs between all molecules. It's sort of a universal attractive force. It increases in strength with the number of electrons, molecular weight, and the number of atoms in the molecule. Now you may say those are redundant terms. Not quite, because each of these terms has a slightly different effect on the strength of London forces. Further, and this is really important, this is our first connection to a central theme in organic chemistry, these London forces depend on molecular shape. Molecules that are compact with less atoms have weaker London interactions, even for the same molar mass. So a classic example of this is if we compare, for example, oxygen, which has a molar mass of about 32 gram per mole. If we compare oxygen to, for example, argon, which has a molar mass of about 40 gram per mole, we would find that because argon only has a single atom, we cannot distribute our electron density over as many atoms. We can't generate as large of a temporary dipole, as large of a separation of charge, and we don't have as large of a surface area for interactions. And as a result, noble gases such as argon, in general, have very weak intermolecular forces and very low boiling points. That's why the noble gases overwhelmingly exist as gases. Let's unpack this idea of molecular shape, and let's impact this idea of temporary dipoles. So suppose we have two molecules, and at any given time, we have electrons distributed throughout each of our molecules, right? Now, at any given time, we can have a temporary random motion of our electrons, and in turn, that would result in our electron density no longer being evenly distributed in our molecule. So let's suppose from the random motion of electrons, we end up with an excess of electron density on one side of our molecule. That in turn will build up a partial negative charge. This is a temporary dipole. And in turn, from this temporary dipole, it will in turn affect the distribution of electron density in adjacent molecules. Our electrons will begin to accumulate in order to get closer to this source of partial positive charge, and in turn, we have generated a second temporary dipole. We now have an attracted interaction between two temporary dipoles, and this is the backbone of London forces. It's a temporary dipole-dipole interaction. And this dipole-dipole interaction only lasts for a matter of picoseconds, nanoseconds. And so we only have this temporary interaction occurring for a very short amount of time, and that's why these London interactions are so weak. Does this idea seem familiar to everyone? Does this idea of London forces seem familiar to everyone? Okay, so building on this idea of temporary dipole-dipole interactions, London forces have a dependence on molecular size. As the molecules get larger, our dispersion forces increase in magnitude. Quite simply, the more atoms we have, the more electrons we have, the more we can distribute our electron density over multiple atoms. We can lead and generate a larger molecular dipole over a larger area. And as a result, we have a stronger attractive interaction because in our larger molecule, we have a greater surface area for interaction. And as a result, we can engage in stronger London interactions. So larger molecules with more atoms and a larger surface area exhibit stronger London forces and have larger boiling points. Does this idea make sense to everyone? Now, we can actually see this. We can actually look at a few case studies. One moment, let me go back to the page we're at. Sorry about that. There was a small lag in our connection. Let me return to the page we're at. Allow me one moment, just so that way the Zoom call can sync up with the screen that I am projecting. Okay, so let's look at how London forces vary for different organic molecules, first as a function of molar mass. So larger molecules have stronger London forces and in turn, larger boiling points. So we can look at boiling point as a function of molar mass, where boiling point serves as a clear result from strong intermolecular forces. The stronger your London interactions, the larger your boiling point. And as we look at this graph of molar mass versus boiling point, what do we see? As our molar mass increases, as we have a larger molecule with more atoms, what happens to our boiling point? Does our boiling point increase or decrease?
Increases.
It increases. Exactly right. Exactly right. So we see a clear relationship between boiling point and the strength of intermolecular forces and molar mass. Okay, now to touch on this idea of intermolecular forces and molecular shape from a case study perspective, if intermolecular forces fundamentally are based on the distance between molecules, the closer your particles are packed, the stronger your intermolecular forces. So if we think about molecular shape, in general, molecules with ordered linear shapes can pack closely together, resulting in stronger intermolecular forces. So molecules with branching shapes or irregular shapes cannot pack efficiently, and in general, we see weaker intermolecular forces. Now, to look at an example of this and to summarize this discussion, in general, the more surface-to-surface contact we have between our two molecules, the stronger our attractive interaction and the stronger our London interactions between molecules. Linear structures, as a result, because they have a larger surface area for interaction, in general, have higher melting and boiling points than branched structures. And we can see this quite clearly if we compare our linear molecule of pentane with our branched molecule neopentane. And as we notice, which substance, which constitutional isomer in this case which constitutional isomer has the higher boiling point and the stronger intermolecular interactions, the linear or the branched. What was that?
Pentane, the linear?
Yep, the linear form has the stronger intermolecular forces, and as a result, has the higher boiling point. Does that make sense to everyone? Perfect. Any questions on this example? Okay, so let's keep going now. And let's talk about a special case concerning cyclic compounds. Cyclic compounds have higher boiling points than their acyclic isomers. So for example, cyclohexane has a boiling point of around 81 compared to hexane's boiling point of around 69. So it's a pretty appreciable increase in boiling point. And part of the reason for this is if we think about, if we write out and we draw out our cyclic structures in a more representative format, one benefit of cyclic structures is that we can get very efficient packing and surface to surface interactions. And that in turn leads to strong London forces. Does that make sense to everyone? So here we see another case where molecular shape has a substantial effect on physical properties such as boiling point. So it's not just dependent on the number of atoms in the molar mass, but also how your molecules can interact and the surface area available for molecules to interact. Does this make sense to everyone? Any questions on this idea? So we're going to apply what we've learned now, and we're going to take a moment and we're going to look at these two examples. So we have example 1 and 2. So we have A and B, or A and B, and then C and D. So for example 1, I'd like you to tell me which of these two molecules would have the higher boiling point? Which of these two molecules would have stronger London interactions? And I'll wait a moment just to allow students to type in the chat. Which of these two molecules, A or B, would have the higher boiling point and stronger London interactions? See a lot of students typing B. That's exactly right. This molecule has a larger molar mass. In the next example, we're comparing a linear and a linear structure with a double bond. So it's a linear, irregularly shaped structure compared to a cyclic structure. And as we discussed, cyclic structures in general have higher boiling points. So we'd select response D. Cyclic structures in general, they have a larger surface area for interaction, in turn, stronger London interactions, and as a result, a higher boiling point. Does that make sense to everyone? Okay, let's look at a few other examples. So let's look at these next three examples, and I'd like you to tell me which substance would you expect to have a larger boiling point? And I'd like you to tackle these three examples, and then we'll discuss these three examples in about 3 to 4 minutes. So let's try to get some responses in the chat, and then we'll discuss in about 3 to 4 minutes. So let's try to get some responses in the chat for these three sets of molecules. And you may want to try drawing out the structure for each of these molecules and indicating which of these molecules would have the larger boiling point. And we'll discuss this example in about another 1.5 to 2 minutes. C6H14 is linear, just like C5H12. They're both linear. And the responses I see in the chat look great, so let's discuss. So first, iodine wins out over chlorine because it has a larger molecular weight. Nitrogen wins out over argon because for nitrogen, we have more atoms, and in turn, we have a greater surface area for interaction. And C6H14 wins out because we have a larger molar mass. Perfect. And the responses I see in the chat look great. Do these examples make sense to everyone? Perfect. So now we're going to add a little bit of sophistication to our discussion, and we're going to consider the next type of intermolecular force. Dipole-dipole intermolecular forces. So these are interactions between the molecular dipoles of two polar molecules to give a strong attractive interaction. So as we notice, the partial negative portion of our dipole is attracted to the partial positive portion of another dipole. So key thing here, dipole-dipole interactions only occur if we have polar molecules. If we don't have a molecular dipole, these interactions do not occur. Further, dipole-dipole interactions increase in strength as we have a stronger dipole. So for example, hydrochloric acid, the hydrogen-chlorine bond is polarized towards chlorine, and in turn, we have an interaction between our two polar molecules where our partial positive region and our partial negative region of each of these two molecules are attracted to each other and are stabilized by this attractive interaction. Does this make sense to everyone? Does this look familiar to everyone so far? Any questions so far? Now, when we think about intermolecular forces and boiling point, let's look at the effect of dipole moment, which is a measure of molecular polarity on boiling point. Now, dipole-dipole intermolecular forces are way stronger than London forces, and as a result, polar molecules generally have higher boiling points. Further, as we see from this graph, dipole-dipole intermolecular forces and boiling point increase with dipole strength. So first, let's look at each of these examples. So we have boiling point as a function of dipole moment, which is a measure of the overall molecular polarity. So we have propane, which is non-polar, has no molecular dipole moment. If we compare it to diethyl ether, already we see a substantial increase in boiling point going from a non-polar to a polar molecule. And this comparison works because all our molar masses are about the same, so our London interactions will be about the same. Note, you can only really do this kind of apples to apples comparison if your molar masses are close to each other. If you start comparing a large molecule that's non-polar to a small molecule that's polar, then the London forces begin to have a greater effect. So within about 10 molar mass units, that's close in terms of molar mass. So as all of these molar masses are pretty close to each other, we can really see that as we increase our overall molecular polarity, as we start to incorporate more polar functional groups, in turn, we have a larger molecular dipole and stronger dipole-dipole interactions, which in turn leads to a larger boiling point. Does everyone see that trend from this graph? As our dipole moment increases, our boiling point increases. Perfect. Any questions on this example? Okay, so let's keep going now. Now, let's look at some examples and let's entertain the following possibilities. Now, remember, dipole-dipole forces fundamentally depend on your molecular dipole. So my question to all of you is, looking at these first two molecules, which of these two molecules will have a stronger molecular dipole? Which of these two molecules in this first example will have a stronger molecular dipole? And you really want to consider from vectors, if we think about our two bond dipoles in this molecule, they're almost pointing in almost opposite directions. In the second molecule, both of our bond dipoles are generally pointing in the same direction. Since this second molecule has a stronger molecular dipole, it in turn would have a higher boiling point. Now, this second example is really cool because we've seen it before, right? And if we look at each of these molecules, which of these molecules would have a stronger molecular dipole? A or B? The
A.
cis or trans isomer? And what was that?
A. The
Yep,
cis.
exactly. The cis isomer actually has a net molecular dipole. It's a polar molecule. The trans isomer, even though it has polar bonds, the dipoles cancel and we have a net non-polar molecule. In turn, the cis 1,2-dichloroethane isomer has a larger boiling point because it has a larger molecular dipole. And we'll see a lot of examples like this where one of our isomers, in this case one of our stereoisomers, has a different molecular dipole and in turn has different physical properties such as boiling point. Does this example make sense?
Yep.
So remember how we considered that we need to add up all of our bond dipoles to get our molecular dipole, and that's because the strength of our molecular dipole directly impacts molecular polarity, which directly impacts the strength of dipole interactions and our boiling point for polar molecules. So you have to be on the lookout for these kinds of symmetry effects. One moment, there's a small amount of lag in the stream. So the last intermolecular force is hydrogen bonding. Now, hydrogen bonding can be thought of as a very strong intermolecular interaction between a highly polarized hydrogen atom and an electron pair on a very electronegative atom. It can be thought of as a ZH bond, where Z is nitrogen, oxygen, or fluorine. So it can be an NH, OH, or FH bond. Now, the hydrogen bond acceptor is the electron pair on nitrogen, oxygen, or fluorine. So it's the lone pair. The lone pair is the hydrogen bond acceptor. The hydrogen bond donor is the hydrogen atom attached to the ZH bond. So the donor would be this hydrogen atom in our OH bond. We indicate hydrogen bonds using either dashed dotted lines or vertical lines, and the hydrogen bond is drawn between our acceptor lone pair and our donor hydrogen atom. Does this look familiar to everyone?
Yeah.
Perfect. So hydrogen bonding is a very strong intermolecular force, and it has a pretty dramatic effect on physical properties such as boiling point. So now hydrogen bonds are much stronger than dispersion and dipole-dipole forces. Substances that can undergo hydrogen bonding have higher boiling and melting points compared to similar substances that cannot. Now, additionally, molecules can potentially form more than one hydrogen bond if they have more than one hydrogen bond donor or acceptor. Note you need both a hydrogen bond donor and an acceptor to form a hydrogen bond. So for example, in water, H2O, we have a total of 2 donors. We have a total of 2 hydrogen atoms, and we have a total of 2 acceptors, 2 lone pairs. This is really why water has a pretty dramatic and a very high boiling point for such a small molecule, because water is able to engage in not just 1, but 2 separate hydrogen bonding interactions per molecule. This is why water has such a high boiling point, because it's engaging in multiple hydrogen bonding interactions. Does that make sense to everyone? Perfect. So let's keep going now. And I'd like you to tell me which of these 2 substances would have the higher melting and boiling point. Ethanol, which has an alcohol or an OH functionality, or dimethyl ether, which has an ether functionality and looks something like this. This ROR functionality is known as an ether. Based on our discussion, which of these 2 substances
The
would have,
dimethyl ether,
would you be able to provide an explanation?
because it has the 2 lone pairs accepting.
So it has acceptors, that's correct. Does it have any donors? Does dimethyl ether have any hydrogen bond donors?
Ah, I see.
So you are correct in noting that dimethyl ether does have hydrogen bond acceptors, but it doesn't have any hydrogen bond donors. If we look at ethanol, is ethanol able to engage in hydrogen bonding? Does it have both a donor and an acceptor? Yes. So as a result, ethanol has a substantially higher boiling point than dimethyl ether. Dimethyl ether has primarily dipole-dipole interactions, while ethanol can participate in hydrogen bonding, and in turn, ethanol would have a higher boiling point. So even comparing 2 molecules with the same number of atoms, depending on the arrangement of atoms in that molecule and depending on the functional groups, we have dramatically different physical properties. Did that example make sense? Any questions on this example? So just remember, for hydrogen bonding, we need both a donor, a ZH bond, and an acceptor, a lone pair on an oxygen, nitrogen, or fluorine atom. Did that clarify this example? Did that make sense? Perfect, perfect. So let's try again this time, and let's ask the question, which of these 2 molecules would have the higher melting and boiling point? Water or ammonia? Which of these molecules would have the higher boiling point? And remember, for when counting hydrogen bonds, you need both a donor and an acceptor. Let's try to get a few more responses in the chat to help facilitate this discussion. And don't be shy to share your response, even if it differs from your classmates. provides me a lot of data into what the class is thinking and can help me structure my feedback. So I see a lot of responses aiming towards water, and that is correct, but let's talk about why that is. So water, we have 2 donors and we have 2 acceptors. While in ammonia, we just have 1 donor. So ammonia can form 1 hydrogen bond, while water can form 2 hydrogen bonds. So in turn, water would have the higher boiling point. Does that make sense to everyone? Does that logic make sense? Ammonia has a lower boiling point by roughly by at least 50 or 60 degrees. So yes, this lone pair does count as an acceptor. Whoops. So we have 1 acceptor and we have 3 donors. And because we have 1 acceptor, we can only form 1 hydrogen bond. Less hydrogen bonds, weaker hydrogen bonding interactions, lower boiling point for ammonia compared to water. Any other questions on this example? If not, let's keep going now. The last intermolecular force is the ion-dipole interaction. We don't see this a lot in organic chemistry, but it's important to consider because it can help us understand a little bit about the role of cations in organic reactions. So in this case, our dipole, we have an attractive interaction between a polar molecule and a charged ion. So we have an attraction between our dipole and an ion. In this case, the partial positive region of our water molecules is interacting with and stabilizing our negatively charged ion. Ergo, the name ion-dipole. This is how ions are stabilized and solvated in solution. Not too much to say here. Any questions on ion-dipole interactions? Any questions on this? If not, let's keep going now. And let's do some examples. So first, here's a summary of all the intermolecular forces. Remember, hydrogen bonding is one of the strongest intermolecular forces. London or dispersion forces are some of the weakest. So let's take a look at some examples and let's indicate which of the following compounds will have the larger boiling point. So I'll do the first example and you'll do the second. So looking at these 2 molecules, so I have a linear molecule compared to a branched molecule. And would someone like to help me out here? Which compounds in general have the higher boiling points? Linear or branched molecules? Linear, yep. So we'd circle the linear molecule on the right. Okay. Now I want you to tackle the second set of examples. So we'll label these 2 and 3, A, B, C, D. And I'd like you to tell me which of the following set of compounds has the larger boiling point. And I'd like you to spend 2 to 3 minutes on this example. And I'd like you to share your responses either in the chat or verbally. And if you're unsure, don't be shy to ask a question in the chat or verbally. Let's try to get a few responses in the chat. And we'll discuss in about 3 minutes. And when you're comparing C and D, I'd like you to just think and write out the factors and write out the factors that make you choose C or D as your response. And just as a reminder, what do we need for a hydrogen bond? We need a donor and an acceptor, right? So let's consider that, and let's see some additional responses in the chat, or some revisions if you have a revision. And we'll discuss this example in about another 1.5 to 2 minutes. And don't be shy to share your responses or revised responses in the chat. And we'll discuss in about another minute. Okay, so let's discuss this example. So in problem 2, we have 2 molecules. In the first case, we have one hydrogen bonding motif where we have one alcohol that can form one hydrogen bond. In our second structure, we have 2 alcohols, so we can form 2 hydrogen bonds. More hydrogen bonds, stronger intermolecular forces, higher boiling point. So B would be correct. Looking at problem 3, my question to all of you is, which of these 2 molecules has a larger molar mass? Which of these molecules has a larger molar mass? D. So molecule D has a larger molar mass. Both of these molecules are relatively polar. And remember how I said that you can only really compare if the molar masses are close to each other? Because if we have a large molar mass in one of our molecules, which molecule will have the larger London forces, C or D? Which of the molecules will have a larger set of London forces? Molecule D, that's correct. So as these molecules are both relatively polar, both of these molecules are participating in reasonably strong dipole-dipole interactions. Our tiebreaker is the fact that sulfur is so much heavier than oxygen that our increase in molar mass leads to appreciably larger London interactions and in turn a larger boiling point. Does that make sense to everyone? So remember, molar mass plays a role if the molecules have a substantial difference in molar mass and have very similar intermolecular forces. Let's do one more set of examples. So I'll do the first example and you'll do the next 2. So we're asked, which of the following compounds has a larger boiling point? So acetone, we have primarily dipole interactions, while acetic acid, we can form hydrogen bonds. And as a result, acetic acid would have a higher boiling point. Let's work on the next two problems. So problem number 2 and 3. I'd like you to spend 2 to 3 minutes on these examples, and I'd like you to tell me which of the following pairs would you expect to have the larger boiling point, and which of the following pairs in question 3 would you expect to be most polar. And we'll discuss these examples in about 2 to 3 minutes. And let's try to get a few more responses in the chat, and we'll discuss in about another minute to a minute and a half. And thank you for sharing your responses in the chat. This has been wonderful to see. And I really like that you're also justifying your points and justifying your assignments in your responses. So it looks like we have a wonderful pool of responses, and they're all spot on. So for 2, phenol can form hydrogen bonds, while benzene is stuck with London interactions. Hydrogen bonding interactions are stronger than London interactions. So compound B would have the higher boiling point. In terms of polarity, again, we consider molecular symmetry. So molecule C, the dipoles cancel. So here we see a link between molecular shape and polarity, which directly impacts our molecular polarity. Compared in molecule D, our dipoles add, and we have a net dipole that is reinforced because both of our chlorines are on the same side of our molecule. Does that make sense? So let's do a capstone example. I'd like everyone to take a look at the following example. Let's take about 2 minutes, and I'd like you to tell me why 1,4-dioxane is a relatively non-polar solvent, while tetrahydrofuran is a relatively polar solvent. So let's take about 1.5 to 2 minutes, and let's try to offer an explanation. Why is tetrahydrofuran substantially more polar than 1,4-dioxane?
Is because the dipole forces cancel out.
Exactly right.
And then the tetrahydrofluorine has a net dipole towards oxygen because it's electronegativity.
Exactly right. And the dipoles don't quite cancel out because dioxane actually looks something like this. So it has some 3D shape, but the dipoles partially cancel. But your logic is perfectly correct here. And that leads to a very weak molecular dipole compared to in tetrahydrofuran, where you have a very strong molecular dipole. Does that make sense? And the reason why I like this example is it also highlights a difference between flat and sp3 hybridized molecules. Because 1,4-dioxane has some 3-dimensional shape, it's not just flat, the dipoles don't completely cancel. So 1,4-dioxane is very slightly polar. Compared to, in this dichlorobenzene example, this molecule is non-polar. So again, we have another link between molecular shape as a result of hybridization and molecular polarity. Does that make sense?
Yes.
Perfect. So we'll stop here for today. We're going to definitely finish up chapter 1 next class session, and I'd like you to bring the chapter 2 notes with you to next class session, as we're definitely going to start chapter 2 on Thursday. So we'll finish up this chapter. We only have a few more pages to go, and then we will start chapter 2 on Thursday. So I'll stop the recording for today.